Hello, my name is Eric Yang, and I'm a Lehigh University student studying computer science and business in electrical engineering. I would like to present to you my project called Versatility of Homomorphic Encryption Scheme within Healthcare Implementations. Now, what is homomorphic encryption? Homomorphic encryption is an encryption scheme that one can perform mathematical operations on encrypted data without having to decrypt any part of it, essentially keeping it guarded throughout the entire process. Every homomorphic encryption scheme follows the same four operations, being key generation, an operation that generates a secret and public key pair, encryption, an operation that takes in the ciphertext and encrypts it, decryption, an operation that takes in the ciphertext and decrypts it, and evaluation, which takes ciphertext as input and outputs a ciphertext corresponding to a function plaintext. Now, the big thing I wanted to tackle is the ability to effectively maintain privacy and security of patient data in healthcare systems. Patients understand that they lack control over the data once it enters the cloud. And by digitizing these valuable and sensitive information, it makes them prone to multiple cyber attacks and other risks. Therefore, I want to propose a question. How can healthcare industries utilize privacy-preserving machine learning techniques such as homomorphic encryption schemes in order to create a prediction model to find correlations between health triggers and illnesses? I wanted to find out if one can perform different types of data analytics, such as correlation analysis on patient health history, and find trends between their history and their illnesses while still maintaining the privacy and security of their information. I chose homomorphic encryption scheme over any other encryption scheme because this technique allows for the collection and sharing of patient data across various locations while still maintaining privacy and security. Now, in terms of how I did it, I first collected different health data from multiple data sets, all sourced from Kaggle, which then I wrote code which let those data underwent horizontally partitioned learning to maintain patient privacy. This process involves strict privacy constraints that confine records within individual clients and encrypt shared information. Collaboratively, linear regression with gradient descent is utilized in the model building process, ensuring the safeguarding of sensitive patient information. Now, the objective of mine is to build a model collaboratively across hospitals without sharing individual patient records or derive information between hospitals. The privacy constraints include keeping patient records within each hospital, encrypting any shared information, and preventing any party from inferring where a patient was treated. Linear regression is used with gradient descent, and each hospital computes its gradient, encrypts it, shares, and sums it with other hospitals, and sends the aggregated gradient to the server. The server then obtains the gradient of the complete data set, decrypts it, and sends it back to each hospital for updating their local models. Now, in terms of result, in the simulation, each client, in this case the hospital, performs a correlation analysis on the same data set, focusing on variables like glucose and blood pressure in this case. The correlation analysis result from each client are then averaged to compute a final correlation coefficient. This coefficient, along with mean squared error, is displayed in a table showcasing the performance of different datasets in the model building process. So as you can see by the table, I have the name of the dataset, the x and y value, which I want to find the correlation between, the mean squared error, and a correlation coefficient. So we can see that there's a positive correlation between smoking cigarettes and attempted suicide, a negative correlation between sleep duration and stress level, and a positive correlation between glucose and blood pressure. So in terms of security, even with the access to the aggregated gradient, no participant can determine the origin of patient's data. So what I would like to see in the future is further implementations and applications of homomorphic encryption. This is due to it being so versatile that it has a possibility of reaching in various domains such as health data analytics, medical imaging, genetic data protection, telehealth, and integration with blockchain technology. There's already an urgent demand for easily accessible and efficient secure computation technology, especially with the shift toward cloud storage and computing by both companies and individuals. Expectations are high for the widespread adoption of homomorphic encryption in healthcare due to its transformative potential. By providing a robust data security while enabling analysis and collaboration, homomorphic encryption is anticipated to play a pivotal role in revolutionizing healthcare practices. And with the continuous growth of technological advancements, the possibility of homomorphic encryption schemes being much more efficient and readily available to not only healthcare but globally in every branch is just upon the horizon.